We now begin our chapter on thermochemistry. And before launching into this topic, let's have a little mood music and images.
The heat is on the streets, inside your head, every beat, yeah, the beat's so loud, and you can say, the pressure's high, just to say.
Okay, thermochemistry. Let's see what this is all about. We'll learn about heat, we'll learn about work, perhaps a little bit of entropy, first law of thermodynamics, specific heat, etc. Okay, thermochemistry deals with energy changes associated with chemical reactions and phase changes. So what is energy? Well, you've probably learned the definition. Energy is the ability to do work, which then prompts you to ask the question, what is work? Work is defined as a force times a displacement. Work is equal to force times d, some generalized force and generalized displacement. Now, the application of this equation that we're most familiar with is moving a mass against the force of gravity, where F is the force of gravity and d is the distance that we've moved this object, for example, lifting a weight. But work could also be done by compressing a spring or a container of gas. Work can be done by moving charged particles against an electric field, or moving a magnet against a magnetic field, or moving a substance against its concentration gradient, or, in the area of chemistry, converting a substance to a less stable substance. These are all types of chemical work. We also often talk about potential energy and kinetic energy. Potential energy is energy that is related to a position against this field, such as the field of gravity. You see our young fellow at the bottom where he has lifted a weight. Once he has lifted this weight, the weight then has stored potential energy due to the position above the ground. Kinetic energy is energy related to motion. You all no doubt remember the equation. Kinetic energy is equal to 1/2 mv squared. M is mass of an object, v is its velocity, and then you square it. We also have heard about, or will at some point, no doubt, talk about atomic or nuclear energy, radiant energy, thermal energy, which we'll talk about in this chapter, and chemical energy. But first, let's define a few terms. Let's define system and surroundings. A system is the material, the matter, that is under consideration. I usually talk about it as what's inside the box or the test tube that you're studying. And everything else is the surroundings, and those surroundings extend to the universe. There are three types of systems: an open system, a closed system, and an isolated system. Now, actually, the definitions of these terms makes common sense. An open system is like a test tube or a cup without a lid on it. That matter and energy can be transferred back and forth between what's inside the test tube or the cup and the surroundings. And this transfer back and forth applies not only to matter, but also to energy in the form of light or heat. A closed system, then, is one in which you have a cork or a lid on the container, so that matter cannot flow back and forth between the system and surroundings, but energy might flow back and forth. Energy in the form, again, of heat or radiant energy. And finally, we have an isolated system, which you can imagine as your cup or test tube surrounded by a thermos or styrofoam. It's completely isolated from the surrounding, so that neither matter nor energy, radiant energy or thermal energy, can flow between the system and the surrounding. It's important to have these definitions in mind because in a minute we'll define the first law of thermodynamics, and you'll see that the term isolated system is a key part of that definition. Before going further, let's talk about how we measure energy. Energy is measured in units of either a joule or a calorie. We'll probably use joule a little bit more, but we sometimes will use calorie in this course. A calorie is defined as the amount of thermal energy required to elevate 1 gram of water 1 degree centigrade. So you can imagine 1 gram of water, and again 1 gram is approximately a milliliter of water. So imagine a milliliter of water, which is not a very large amount. It's the amount of water that would fill a cap of a Bic ballpoint pen, although this is this cap is a little bit larger than that. And it's the amount of energy needed to raise that small amount of water 1 degree centigrade, between 14.5 and 15.5 degrees centigrade to be technical. So that's our definition of a calorie. The other unit that we will use quite often is a joule, which was named after James Prescott Joule. And the relationship between a joule and a calorie is shown in this slide. 1 calorie is equal to 4.184 joules. So that means a joule is a smaller unit because it takes 4.18 of them to be equal to 1 calorie. Now, James Prescott Joule was an Englishman. He was a physicist. He's a brewer and a businessman, and he studied heat and the relationship to mechanical work, and he helped formulate the first law of thermodynamics, which we will now give to you. The first law of thermodynamics states, hear that drum roll? In an isolated system, see, a system that is completely isolated from its surroundings so that neither energy nor matter can flow back and forth between the surroundings and the system. In an isolated system, the total amount of energy, including heat, or what we will often call thermal energy, the total amount of energy is conserved. A corollary of this first law of thermodynamics, we oftentimes state, is that in an isolated system, energy is neither created nor destroyed, but it can be converted from one form to another. Okay, now in this slide we talk about thermal energy and a concept called heat capacity. Thermal energy is a form of heat that flows from a hotter to a colder object. And at some point we might refer to thermal energy as dissipated energy. But let's stick with this first definition to begin with. Thermal energy is the form of energy that flows spontaneously from hot to cold. You might imagine, if you see at the bottom right of this slide, when you take an iron poker and you heat up one end, what happens? After a while, that thermal energy will be conducted to the other end of the iron poker. Thermal energy spontaneously flows from hot to cold. We know now that thermal energy is related to the motion of molecules. But let's consider, if you have a glass of cold water at 5 degrees centigrade and a glass of warm water at 50 degrees centigrade, which one possesses the most thermal energy? Well, it's pretty obvious. The one that is at a higher temperature will possess the most thermal energy. But otherwise, if we just looked at our glass of cold water and hot water, unless we could see some moisture condensing on the side of one, it would be hard for us to distinguish them without using a thermometer or, again, seeing something like the condensation. But one contains more thermal energy, obviously. Now, the amount of thermal energy possessed by a substance depends upon its temperature, obviously, but also on the nature of the substance. And this is what we refer to as the heat capacity of a substance. And we sometimes use the term specific heat capacity. When we say specific in chemistry, we mean per gram, but we also mean specific to that substance, but we mean per gram of that substance. So let's talk about the specific heat capacity of a substance. How much thermal energy is needed to raise the temperature of a mass M of some substance, let's say iron, from 30 degrees to 40 degrees centigrade, just to heat it up by 10 degrees? This type of problem is a specific heat problem, and we need to know the specific heat capacity of the substance iron. For example, the specific heat capacity of water is actually embodied in the definition of a calorie. Remember, we said that a calorie is the amount of thermal energy needed to elevate 1 gram of water 1 degree Kelvin, or 1 degree centigrade, because the step sizes are the same for Kelvin and centigrade. Or that would be 4.184 joules, would be the amount of energy in joules needed to elevate 1 gram or 1 milliliter of water 1 degree Kelvin. For iron, the specific heat happens to be 0.45 joules per gram per Kelvin. So the specific heat of iron is a lot less, 0.45, a lot less than the specific heat of water, which is 4.184. So that tells you something. It takes more thermal energy to increase the temperature of water than it does of iron. It takes almost 10 times as much because the specific heat is 10 times larger. Okay, so if we wanted to be exact about this, we would actually plug into this equation. Specific heat is equal to the amount of thermal energy, Q. That is, our symbol for thermal energy is going to be Q. Backing up, specific heat is equal to Q, the thermal energy, divided by the product of the mass times the temperature change. Okay, so going back to the question we were asked, how much thermal energy, Q, is needed to elevate a certain mass of iron, M, by a certain delta T, which in this case is 10 degrees. You can see from this equation that if we know the specific heat of iron, 0.45 joules per gram per degree Kelvin, and we know the mass, whatever the mass is, and let's say in this problem it's 50 grams of iron, and we know the delta T that we're shooting for, 10 degrees centigrade, we simply rearrange this equation and plug in to solve for Q. And we will determine then that the amount of thermal energy, if you see at the bottom, is 225 joules. That's the amount of thermal energy that would needed to be added to that 50-gram block of iron to increase its temperature by 10 degrees, from 30 degrees to 40 degrees centigrade. Okay, we're going to pause at this point, and then we'll come back and continue our discussion of specific heat.